2 million. There are 2 million people flying in the air right now, and almost all of these flights are powered by kerosene-fueled gas turbines, and that contributes to around 4% of global warming. And looking ahead, we see that air travel is booming. By 2050, passenger numbers will be double what they are today. And with current technology, emissions will rise, and the global carbon budget cannot accommodate this. So what are we going to do? What is the aviation industry going to do? Well, the most attractive option for removing carbon from the aviation industry would be to remove carbon from the fuel itself. This means developing new propulsive technologies that work on hydrogen or electricity derived from renewable energies. There are limitations, though. If we look at electric-powered aircraft, they're reasonably easy to implement, but they only work for small aircraft going short distances. Whereas hydrogen scales well for our typical long-range, large passenger number flights. But there are many challenges left to be addressed with this technology, and the supplies of truly renewable green hydrogen are limited. And for these reasons, the aviation industry estimates that around 25% of the carbon that we need to remove by 2050 can be achieved by developing these new zero-carbon propulsive technologies. Another 25% will come from implementing new operations, that is, flying slower and rerouting flights to minimize climate impact rather than speed. And this is a really attractive option because we don't need to develop new technology to do this. We could do this today. The issue here is that airliners prioritize time and other commitments that they have rather than implementing this. So we need policymakers to enforce measures for green operations over the next 10 years to be able to remove 25% of our global, to remove 25% of the carbon being produced by the aviation industry. And that leaves 50%, and that 50% will be made up by implementing sustainable aviation fuel in basically conventional gas turbines that we have today. Sustainable aviation fuel, or SAF for short, is kerosene manufactured from biomass and waste oils. And using SAF is a little bit like swapping out cow's milk for oat milk. So there is still some climate impact, but it's closer to being carbon neutral. The issue that we have, and why there's still impact with SAF, is it requires large amounts of agricultural land for its production. So even as we transition from using only kerosene to using SAF, we need to continue to develop more efficient aircraft engines. So let's take a look inside a gas turbine, and in doing that, I can tell you about the work that we do at the Oxford Thermofluids Institute to make these engines more efficient. So if we look at the aircraft engine, there are four main modules. We have the turbofan, the compressor, the combustor, and the turbine. Now, the turbofan is what your attention is normally drawn to as you're boarding the aircraft. It's a large spinning fan at the front. This generates almost all of the thrust for the engine, draws in a huge amount of air. What powers the fan? Well, we burn fuel in the combustor, and those combustion gases expand aggressively through the turbine. And as they expand through the turbine, they cause it to spin. The turbine is connected by a shaft to the turbofan, and that powers the turbofan. How do we make that process more efficient? Well, we actually already know how to do this. That's why the compressor is ahead of the combustor. We use the compressor to compress the air as much as possible before doing the combustion. That allows us to extract more useful work from the combustion process. But therein lies a problem. As we compress the gas, we go from a large volume to a small volume. Can anybody tell me what this does to the air temperature? Yes, it increases. And for a modern gas turbine with a compression ratio of around 50, this actually triples the air temperature before we've even done the combustion. So once we do the combustion and those gases are going into the turbine, it is around 1700 degrees centigrade. That is an unimaginably hot temperature, so I have two reference points for you. The first is that lava is around 1000 degrees centigrade, so this is way hotter than lava, the hottest thing that most people can think of. Secondly, the more important reference point is that this is much hotter, 300 degrees hotter, than the melting point of our most advanced aerospace metal alloys, which melt at around 1400 degrees centigrade. So how do we stop the turbine from melting? We cool it. We cool the turbine components. So one of the important components in the turbine is the turbine blade, and we make these hollow. And through those hollow passages, we can pass cooling air. That cooling air cools it down from the inside, and then the surface is also pierced with lots of little holes. These little holes kind of look like a shower head, and out of these holes emerges the air. It surrounds the object in a thin film. It's kind of like a protective jacket for our components, and it stops those really hot turbine gases from coming into direct contact with the metal. And the issue that we have with this is that the turbine environment is extremely complex. So all of our components are rotating, and then those combustion gases are kind of expanding aggressively, and that means that they're kind of swirling around like a tornado and fluctuating all over the place. And that means that there are regions that are hotter, we call those hot spots, and so it's then really difficult to design an efficient cooling system that works everywhere all the time, including those hotter regions. What do we do? Well, one method that we take at the Oxford Thermal Institute is to perform experiments. And I want to be very clear with what I mean by performing experiments. Do we take a new cooling design, fit that into an aircraft engine, and get data that way? No, that would be a really expensive, time-consuming, kind of practically very difficult, and it would actually be very hard to get useful data out of that we can use. So the beauty of performing experiments is in one key concept: simplification. We take our real engine and we focus in on the part that we're interested in. We produce a test facility, we call it, that replicates the key conditions present in the turbine that we're interested in. And this gives us the ability to configure it for testing different cooling designs. We can fit instrumentation in there, and we can, kind of go through different designs.
Right. In
that test facility, we fit it with instrumentation. We have all used instrumentation ourselves, at home, a thermometer for taking our own temperature, and many of us now wear a smartwatch. That's instrumentation, and you turn yourself into a walking experiment by wearing one. The instrumentation that we use in our test facility includes high-precision thermometers that we fit to the surface or perhaps inside of the blade that allows us to measure the metal temperature. And we also use infrared thermography. That's an infrared camera, a little bit like how night vision works. It allows us to observe the heat being emitted all over the components. And by bringing that all together, we can work out how effective, how efficient our cooling design is. And at the same time, we run simulations. We run models on a computer of the turbine cooling. And a computer model is, these computer models is very similar to how we predict the weather. So with that, we know what the weather is today, right now, and we use these equations that govern fluid flow to work out what the weather is going to do in the future. The issue here is that these equations are incredibly complex, even for a supercomputer to solve. And so we have to introduce some approximations into those equations. Those approximations, unfortunately, introduce errors, and those errors increase as we go forward in time. And for that reason, the weather is normally accurate for the next 24 hours, but if you go ahead to a week, it becomes less accurate. And we suffer that same problem with our simulations, meaning that we can't trust the results immediately. But we don't have to, because we can set up simulations that replicate the test facility, and so then we've got computational data, experimental data, and we compare the two. And we can work out whether that simulation was accurate, and once it is, we consider it to be validated. And once validated, we now have a really powerful tool, because we can work together with those simulations and run hundreds of different designs, way more than would be achievable if we were only doing experiments. And by doing that, we've been able to create more efficient turbine cooling designs. And over the past decade, the aviation industry has managed to improve engine performance by around 15 to 20%. And we're continuing that into the future. So in summary, decarbonising aviation, there's no single fix. We need to introduce new propulsive technologies that are zero carbon. We need to implement operational changes, and we need to use sustainable aviation fuel. But we're also completely dependent on developing more efficient aircraft engines, and we do that by increasing the temperature in the turbine, only possible because we continue to make our cooling systems more efficient. And so while turbine cooling might seem like a small piece of the puzzle in removing carbon emissions by 2050, it's an absolutely essential part of keeping those 2 million, soon to be 4 million people flying in the air, moving towards a zero carbon future.